Welcome to the first episode of Cryptoshorts, a show not about shorting cryptocurrencies, but about protecting private information with computers and math.
Today we'll talk about elliptic curves and we'll show you how they work with the example of Diffie-Hellman protocol.
Let's start with a classic problem of Alice and Bob trying to communicate over the internet. To communicate safely, they will need to encrypt their messages. And to do that, they would need a shared secret key. But how do they set it up? One way to do that is for Alice to create a key and send it to Bob. But in order to transfer the message with the key securely, they would need to encrypt it somehow. This brings us back to the problem that we started with. So our goal here is to help them generate the shared secret key separately on their own without sending it directly. For that, we'll use elliptic curves.
Elliptic curve is a two-dimensional line. We'll be using Edwards curve that looks like a warped circle. The curve consists of points that we can add. Let's say we have points A and B. Addition of them combines their coordinates to produce a new point C. We can also add a point to itself. So if we add A to itself, we get 2A. If we add it again, we arrive at another point, 3A. Addition works similar to how you add angles on a circle. Turns out, if we add a point many number of times, x, the path to the resulting point, xa, would look completely random. The key feature is that the number x is impossible to guess without trying almost all possible numbers. If someone knows the starting point and the end point, they cannot find the secret factor between them. We will call this starting point generator, the end point public key, and the x number of additions the private key. Now let's use this feature to help Alice and Bob construct a shared secret key.
Diffie-Hellman protocol allows to establish a shared secret key between two parties. As designers of the protocol, we will choose a specific curve and a starting point G. Let's go back to Alice and Bob. First, each of them chooses a random number, a private key that they will never share. These will be indicated by lowercase letters. Then each computes a corresponding public key. This is a point computed by multiplying the starting point G by the corresponding private key. We will use uppercase letters for points. Next, they exchange their public keys while keeping their private keys secret. Alice sends her public key to Bob, while Bob sends his public key to Alice. Now, anyone who observes their communication would only see points A and B, as well as the starting point G. As we just learned, knowing these points is not enough to learn the secret factors between them. The final part is for Alice to multiply Bob's public key by her private key, while Bob multiplies Alice's public key by his private key. The magical part is that they both arrive at the same point S, which is their shared secret. This works because Alice will get A times B number of G's, and Bob will get B times A number of G's. While all other points so far were public, point S is only known to Alice and Bob. This is because in order to compute point S from already known points A, B, and G, one needs to know one of the private keys, A or B. Finally, Alice and Bob will use the x-coordinate of this point S as an encryption key to encrypt and sign their messages.
So to recap, elliptic curve consists of points. Points can be added together, and if they are added many times over, then it's hard to find out how many additions took place. This helps us establish a shared secret using the Diffie-Hellman protocol. Parties multiply each other's public keys by their private keys, arriving to the same resulting point known only to them. This is both the most simple and the most ubiquitous application of the elliptic curve cryptography. Every time you connect to any other computer, your device performs this protocol. In the next episodes, we will show you more fun things that you can do with elliptic curves.